On September 5, 1977, a spacecraft built for 5 years of planetary science launched from Kennedy Space Center. Voyager 1 is now more than 15 billion miles from Earth and running out of power. In 2026, NASA shut down one of its last working instruments. Contact will likely end in the early 2030s, but before it goes silent, Voyager's recovered data has shown something unexpected. Interstellar space is not the calm, empty void we assumed. What those final transmissions actually contain starts with a spacecraft that was never built to last this long. The liftoff from Launch Complex 41 occurred at exactly 12:56 and 1 second UTC. The Titan 3E booster and its Centaur upper stage cleared the pad only after ground crews resolved a pre-launch fuel leak and a computer controller glitch that threatened to scrub the flight. This primary mission had a highly specific scope, a brief reconnaissance of the outer gas giants. Operating indefinitely was never part of the design. Voyager 1's science package, consisting of 10 instruments designed for close-range planetary scans, was never intended to operate in the cold plasma of the interstellar medium. To extend its utility decades past its planned lifetime, flight controllers have had to manage a steadily declining electrical output, executing a disciplined sequence of software modifications, power reallocations, and selective instrument shutdowns. The spacecraft's survival is not the result of automated endurance, but the consequence of adaptive, manual engineering on Earth, where a dedicated team continuously rewrites command sequences to keep the fading systems alive. On April 17, 2026, NASA engineers executed commands to permanently deactivate the low-energy charged particles instrument. Official Jet Propulsion Laboratory records verify this shutdown was a preemptive action to maintain essential voltage margins. This defensive engineering strategy met its most severe challenge on November 14, 2023, when Voyager 1's telemetry suddenly degraded into an unreadable, repeating stream of binary ones and zeros. For 5 months, the spacecraft continued its silent flight, transmitting nothing but garbled code, leaving engineers unable to monitor basic system health or scientific instruments. Ground controllers eventually isolated the fault to the Flight Data Subsystem, which packages the spacecraft's science and engineering data before transmission. Operating with only 80 kilobytes of memory, the system relied on aging components that had survived decades of cosmic radiation. The team discovered that a single deteriorated memory chip, containing a portion of the subsystem's software routines, had failed, corrupting roughly 3% of the computer's memory. Because no physical backup existed for this specific component, the engineering team had to design a software workaround that would relocate the affected code to healthy sectors of the remaining memory. Before sending the command, engineers spent weeks testing the patch on ground-based simulators to ensure the new memory map would not conflict with other critical systems. JPL transmitted the corrective code on March 1, 2024. The commands traveled across roughly 15 billion miles of interstellar space. At this extreme distance, radio signals require over 22 hours to reach the probe, and another 22 hours for the response to return to Earth. This delay forced the engineering team to wait through an approximately 44-hour round-trip communication cycle for any confirmation of success. Operating across this vast void, project manager Suzanne Dodd described the operation as working blind, noting that a single incorrect line of code could permanently silence the probe. The tension ended on April 20th, 2024, when the Deep Space Network received the first readable telemetry from the spacecraft in 5 months, proving the remote software relocation had successfully bypassed the damaged chip. The restored telemetry stream carries data from an environment once assumed to be an empty, inert void. Space beyond the heliopause is actually a highly structured medium. It consists of a sparse plasma, a gas composed of electrically charged particles, interleaved with magnetic fields, waves, and localized density variations. When Voyager 1 instruments register these phenomena, they detect electromagnetic oscillations. Though popular media accounts often translate these signals into audio recordings to capture public interest, they are not sound waves traveling through air. They are purely electrical fluctuations captured by the spacecraft's antennas. Earlier theoretical models predicted this interstellar region would be a calm, uniform expanse. Instead, the incoming data reveals physical turbulence. In this extreme environment, turbulence does not mean meteorological weather, but rather measurable, irregular fluctuations in the density of the charged medium. A critical distinction must be made between temporary isolated wave events caused by solar disturbances and continuous ongoing wave activity native to the medium itself. While identifying the existence of this wave activity is direct and measurable, explaining the physical mechanism that generates it remains an active scientific question. The primary objective is to resolve a fundamental physical inquiry. Exactly how active is the space beyond the Sun's influence? Voyager 1 launched on September 5, 1977, lifting off from Launch Complex 41 at the Kennedy Space Center aboard a Titan IIIe Centaur rocket. The spacecraft carried a 5-year design mandate structured strictly to conduct close-range reconnaissance of Jupiter and Saturn. Operating past those targets was not part of the initial engineering plan. It was an era of rare orbital geometry, a planetary alignment occurring once every 176 years that allowed a single spacecraft to fly from one gas giant to the next using gravity assists. A gravity assist is an orbital maneuver where a spacecraft enters a planet's gravitational field to alter its speed and direction, gaining velocity relative to the Sun without consuming propellant. This alignment allowed engineers to plan a trajectory that would utilize the orbital energy of the giant planets. On March 5, 1979, Voyager 1 made its closest approach to Jupiter. The flyby revealed active volcanism on the moon Io, complex atmospheric wind patterns, and a faint planetary ring system. The Jovian gravity well flung the probe toward its next target. By November 12, 1980, the spacecraft reached Saturn, performing a close flyby of the planet and its largest moon, Titan. This encounter determined the future course of the mission. To study Titan's thick, nitrogen-rich atmosphere, flight controllers directed Voyager 1 on a path that bent 35 degrees out of the ecliptic plane, sending it upward and away from the remaining planets. While Voyager 2 continued on toward Uranus and Neptune, Voyager 1 headed directly toward the outer boundary of the solar system. In 1990, NASA formally established the Voyager interstellar mission, shifting the probe's focus from planetary observation to the outer limits of the Sun's magnetic influence. In August 2006, the spacecraft crossed the threshold of 100 astronomical units from the Sun, moving at over 38,000 miles per hour. The destination was the heliopause. This is not a solid wall, but a dynamic pressure boundary where the outward force of the solar wind balances the pressure of the interstellar medium. The crossing occurred on August 25, 2012, at a distance of approximately 121.6 astronomical units. Confirmation did not come from a single sensor, but from a combination of physical data points. The low-energy charged particle instrument registered an immediate drop in solar particles of over 3 orders of magnitude, while the cosmic ray detector recorded a sudden rise in high-energy galactic cosmic rays. Simultaneously, the plasma wave system detected local electron oscillations at 2.6 kilohertz, indicating a surrounding plasma density of approximately 0.08 particles per cubic centimeter, a density far too high to exist inside the solar bubble. Magnetometer readings completed the picture, recording a stable magnetic field direction consistent with galactic space. This multi-instrument convergence confirmed that the spacecraft had become the first human-made object to reach interstellar space. Project scientist Ed Stone managed this transition as a scientific steward, guiding the analysis of these coordinate data streams to verify the boundary crossing. Voyager 1 had transitioned from a planetary explorer to a functional interstellar station. In mid-2017, the plasma wave subsystem aboard Voyager 1 began registering a weak, continuous, narrow-band emission. Unlike the sharp, transient plasma oscillations triggered by distant solar shocks, this signal persisted as a steady frequency line centered near 2 to 3 kilohertz, with a narrow bandwidth of only 40 hertz. Though often converted into audio tracks for public presentations, these measurements are entirely electromagnetic rather than acoustic. In the near vacuum of interstellar space, there is no air to carry physical sound waves. Instead, the instrument's 2 10-meter antennas detect the electric field oscillations of vibrating electrons. This local plasma frequency acts as a direct mathematical proxy for electron density. Denser plasma produces a higher characteristic oscillation frequency. By converting the detected frequencies, researchers mapped a local electron density of approximately 0.09 to 0.11 particles per cubic centimeter. This persistent signal remained stable across more than 900 million miles of interstellar space, representing roughly 10 astronomical units of travel. In May 2021, the findings were formally published in the journal Nature Astronomy in a paper titled "Persistent Plasma Waves in Interstellar Space Detected by Voyager 1." Lead authors Stella Koch-Acker and James Cordes, along with plasma physics researchers William Kurth and Donald Gurnett, documented this continuous background emission. This steady signal provides a method to monitor the interstellar medium without relying on sporadic solar events. Before 2017, density measurements were limited to rare, shock-driven plasma oscillations. While the exact physical mechanism that generates this steady wave activity remains unqualified and is still actively debated, the small localized density fluctuations measured along the spacecraft's path confirm that the local interstellar medium is shaped by continuous, small-scale turbulence. At the outer boundary of the solar system, the spacecraft also encountered extreme physical environments. Public accounts frequently describe a wall of fire at the heliopause, citing temperatures between 30,000 and 50,000 Kelvin, which corresponds to roughly 30,000 degrees Celsius. In the outer heliosphere, this temperature represents the average kinetic energy of the particles rather than a dense pocket of heat. The very local interstellar medium is a sparse, collisionless plasma where particles are spaced extremely far apart. Because there are virtually no physical collisions between these high-energy ions, the heat transfer to a solid body is non-existent, and the spacecraft's physical structure remains unaffected. While Voyager 1's instruments provided the initial boundary context for these high-energy particles, Voyager 2's functioning plasma spectrometer instrument returned the first direct temperature measurements of this boundary zone during its crossing in 2018, confirming the localized temperature spike just outside the heliopause. The physical mechanism driving this localized heating is magnetic reconnection. This process occurs when magnetic field lines from different systems break, rotate, and join back together, converting stored magnetic energy into kinetic particle energy. Magnetometer data shows that as the solar wind meets the interstellar boundary, this process restructures the solar magnetic field into a complex network of magnetic bubbles, forming a frothy boundary layer in the heliosheath. Some interpretations suggest that this reconnection directly links the solar magnetic field to the galactic magnetic field in a continuous line. However, published analyses present a qualified view. The evidence confirms localized magnetic restructuring and the creation of isolated magnetic islands, rather than a simple continuous magnetic connection. Magnetometer measurements of approximately 5 microgauss on Voyager 1 and 7 microgauss on Voyager 2 show that the galactic magnetic field drapes and deflects around the heliopause, creating a complex, semi-permeable boundary rather than a direct, open conduit. Voyager 1 operates on a finite electrical budget. The spacecraft relies on 3 multi-hundred-watt radioisotope thermoelectric generators, which convert the heat from the natural decay of plutonium-238 directly into electricity. At launch in 1977, these generators provided approximately 470 watts of power. Because plutonium-238 decays at a predictable physical rate, the system loses roughly 4 watts of electrical output every year. Decades of continuous operations have reduced the available energy to a fraction of its original capacity, forcing flight controllers to manage a structural deficit. To sustain the mission, engineers must make deliberate trade-offs, progressively turning off non-essential heaters and science instruments to protect the central systems. The permanent shutdown of the low-energy charged particles instrument on April 17, 2026, was not a sudden component failure, but a strategic power management decision. It was executed to protect the remaining voltage margins and keep the most essential instruments, the magnetometer and the plasma wave system, online. Mission planners face a stark choice: preserve core telemetry and a minimal set of sensors for as long as possible, or run more instruments and risk an immediate, system-wide undervoltage shutdown. This power decline is distinct from the challenges of distance and signal degradation. While the Deep Space Network's highly sensitive ground receivers can still isolate the faint radio signal across billions of miles, the spacecraft itself will eventually lack the electricity needed to run its onboard transmitter. Current NASA projections indicate that the power output will drop below the absolute minimum operational threshold in the early 2030s. There is no predicted single-component failure or exact calendar date for the final contact. Instead, the signal will simply fade into the cosmic background noise. Until that point, every line of telemetry remains a measurable, irreplaceable record from the most distant path ever traversed by a human machine. Today, Voyager 1 remains our only direct data stream from the interstellar medium. As its signal fades toward absolute silence, we face a stark reality. Once this machine goes dark, humanity becomes blind to the deep galaxy. The question is no longer what this 1970s hardware can endure, but when we will build the resolve to follow it. Join the conversation in the comments below.